Hello my dear students, in today's lecture I will start the mechanical rotational system, that is the modeling of mechanical rotational system. Before we start the modeling of mechanical rotational system, in the last lecture we have uh, found the differential equation of mechanical translational system. So first we will find out what is the transfer function of mechanical translational system. After that I will start the mechanical rotational system. So let us start the today's lecture. So this is in the last lecture I have derived the differential equation for mechanical translational system, that is ft is equal to md square xt by dt square plus b dxt by dt plus kxt. So this we can again represent by this system, that is ft is equal to m x double derivative plus b single derivative plus kx. So here by taking the Laplace transform we can find out the transfer function of the system, that is fs is equal to ms square x of s plus bs x of s plus k x of x. So fs is equal to x of s plus x of x is taking common ms square plus bs plus k, that is x. The transfer function, that is output, is the x of x, that is the displacement in frequency domain, and this is the force applied f of s to 1 by ms square plus bs plus k is the transfer function of mechanical translational system. So let us now discuss what is the mechanical rotational system. So let us start today the mechanical rotational system. So in the last lecture already I told what is called mechanical translational system, that is the motion of an object in a straight line, but in this case this is called rotational system, that is here the motion is, that is rotational motion, or that is angular motion of an object is called the mechanical rotational system. That is for example, one will take one motor, that is electrical motor, which rotates in that is rotates in angular motion, and so many examples are there which are rotates in a angular velocity or angular motion, is called mechanical rotational system. This is also having three basic elements. The first basic element is the moment of inertia, and the second basic element is the damper or dash pot, and the third element is the torsional spring. So though these three basic elements having some relation with mechanical basic element, but some differences are there. So let us draw the block diagram of mechanical rotational system. Block diagram of mechanical rotational system. So this is the block diagram of a simple mechanical rotational system. The fixed, this is the fixed end, and this is the object which rotates around a shaft. So when one object starts rotating around a shaft, so let us assume that it makes an angle theta, that is called angular displacement. This is angle theta. Here theta is called angular displacement, and it moves in a velocity is called angular velocity. Here theta is angular displacement. And the velocity, that is called angular velocity. It is denoted by omega, that is angular velocity, and alpha is the angular acceleration, and J is the moment of inertia. So T, that is torque applied to the object, torque applied to the object. Therefore this is the damper where we have taken a viscous liquid or gas, and here the torque applied, that is T, and this is the shaft. Here the shaft is represented by the torsional spring, because when a shaft is subjected to torque, then the torsional, it acts as a torsional spring, that is torsional torque is developed in the opposite direction to the applied torque. That is, torsion means we can easily understand this. So let us assume that this is the shaft. Let us assume that this is the shaft. Then when we'll apply, if one end of this, suppose this end is fixed, and at this end the object is connected to the shaft, and at this end the object is connected to the shaft, then torsion means like this. This is called torsional torque. If the stiffness of the shaft is high, then the torsional torque also develop high. If the stiffness is low, then torsional torque developed is low. Therefore, there is a chance of damaging the shaft if the torsional stiffness is low. So it will be damaged if the torsional stiffness is low. If next we can take this is the shaft, then if this end is fixed and at this end one torque is applied, then the torsion means this is the torsional torque develop in the opposite direction, and if the stiffness is high, it will be rotate very strongly, otherwise it will be damaged like this. This is called torsional stiffness. So here the shaft is represented by a torsional spring, and this is the damper where the object rotates in a viscous medium, that is either liquid or gaseous medium, and this is having moment of inertia J. So now let us derive the mathematical equation for mechanical rotational system. So let us derive the mathematical equation for mechanical rotational system. So first we will analyze one by one. So let us draw the free body diagram for each system. So first let us discuss the moment of inertia. So let us assume that this is having moment of inertia J, and a torque is applied in this direction, that is T of T. Therefore, one angular displacement takes place, that is theta of T. With angular velocity, it rotates with angular velocity omega T. So in this case, what happens when a torque applied to a when a torque applied to a object, then the moment of inertia J of the object produces one angular acceleration. Therefore, immediately a reaction torque develops in the opposite direction, which is the product of moment of inertia and angular acceleration. So here the torque applied is T of T. Therefore, due to moment of inertia of this object, immediately this produces another torque just in opposite direction, that is Tj. This is called reaction torque. Tj is the reaction torque in the opposite direction, which is equal to product of moment of inertia J and that is angular acceleration. So when a torque applied to an object having moment of inertia J, immediately a reaction torque is developed in opposite direction. So that is called inertia torque. Which is equal to product of moment of inertia J and angular acceleration alpha. So Tj is equal to J into alpha, which is equal to J into the alpha, that is alpha is equal to d omega by dt, that is derivative of the angular velocity. So J d omega by dt, which is equal to J d square theta of t divided by dt square. So this is the mathematical equation for moment of inertia. So let us now discuss mathematical equation for damper or dashpot. So let us see the damper or dashpot. So this is the damper. So here we have applied one torque, that is T of t, and it produces one angular displacement theta of t. So let us assume that this side is, that is fixed side. So now let us find the equation of this. When this torque is applied to the piston, then piston moves in angular velocity and it produces a displacement theta of t. Therefore, here the viscous friction becomes the prominent and the static friction and Coulomb friction is neglected. To make the equation linear or to make a linear model, we have to neglect here the Coulomb friction and static friction. Only we have considered here the viscous friction, because here we have taken a viscous liquid, that is your either viscous liquid or gas. Therefore, the viscous friction is the most effective element. Therefore, immediately a reaction, that is viscous torque is developed, that is represented by the TB. Therefore, TB is the viscous torque, which is equal to the viscous coefficient B, and that is omega, angular velocity of the piston, which is equal to B d theta of t by dt. So this is the equation for damper or dash spot. So next we will discuss about the torsional spring. So let us now discuss torsional spring. So this is the torsional spring, that is shaft. So when the torque Tt is applied, it produces